I'm not picking these out of any cunning plan. I honestly can't remember what's in this year's, and I certainly can't remember what's in this year's, so there's no, I'm not trying to mislead or to help in that respect. Okay, well, let's see what we had to just talk about, and then I can go through the solutions on demand, as it were. That is pretty much a direct lift by looking at the problem sheet. The numbers might be different, I'm not sure. But yeah, if you did the first problem sheet in the course, I think you could just work through that quite. And it's bread and butter stuff, isn't it? Work out number densities, work out reaction rates, appreciate the difference between fission rate. And what is the difference between consumption rate and fission rate for 235? Like, why are they different? Yeah, absolutely. It's got a plain old absorption cross-section or a capture cross-section as well as a fission. Absolutely. Spot on. Yeah. So, fine. Draw a chart of the life cycle of neutrons in a critical thermal reactor. Okay, so that's fine. I invite you to put on such approximate numerical values as you can. Again, I think that's perfectly reasonable. You know, they're born at high energies. You may or may not remember the energies, but there aren't many things I try and encourage you to remember. And it's things like there's a 200 MeVs per fission and 2 MeV fission neutron energies, 0.02 EVs, thermal neutron energies, 30 EVs or so for displacements and chemicals. There's not many numbers, but I think they give you a really good set of points to locate yourself in space in that context. Anyway, life cycle. So birth, possibly a few fast fissions, starting to slow down, passing through the resonance region, may or may not get absorbed during resonance. Slow down thoroughly, might get captured uselessly in structure or coolant or whatever. Some will make it all the way into the fuel, and most of those. Sorry, folks. Most of those will actually then cause fissions, and there we have the life cycle of your neutrons. So that's all I was asking about. What is K infinity and the four-factor formula? Again, I hope for most people that'll be straightforward. It's the multiplication factor of an infinite block of our material, and it's fission rate divided by the absorption rate, mu times sigma f over sigma a. And then we have to do a couple of things to allow for the fact actually that we're working in terms of thermal cross sections, because that's when the events are happening, but we're actually generating fission neutrons, but it's the thermal neutrons that are causing the fissions. So we put in a couple of extra terms to try and allow for the fact that there's a hell of a lot of things happen or might happen between being born as a fission neutron and eventually making it. It is like the Stickleback's life cycle, isn't it? Eventually making it or the Lion King, making it to generate his own fresh fission neutrons some little while later. So that's the resonance escape probability and the fast fission factor, trying to take those into account. Would you like? Right. Again, this was just like bits and pieces of quick, easy stuff. Starting from that, not even going back to first principles. Starting from that, so we derive the criticality condition for a sphere. We did that probably last week again. I'm sure you don't want to do it now, but straightforward stuff. Yeah, and this one, yeah, slightly different take on it. So not asking you to solve the criticality, the reflected problem, just to discuss what's different about it, just to make plain that you realise, there's a whole reflector out there now with a similar kind of equation but different, because the K infinity is now 0, and you'll be needing to match boundary conditions at the interface, or match interface conditions, or match conditions at the interface, I guess. Probably finishing off by saying, and the net result of that is it would make the critical radius smaller, because some of the neutrons that did leak now get back, and so plainly that improves the economy. So asking you to demonstrate you understand physically what's going on rather than necessarily than doing more algebraic manipulations. Okay. That goes back to the first question when we talked about the nuclear physics part. So we had that discussion, didn't we? Was it last week, I think? We talked about binding energy and the energy of the incident neutron providing binding energy and activation energy. I think we did last week or the week before. So why we can get some energy out on fission and the energy exchanges. We've got the graph of the binding energy per nucleon with that big steep rise and that broad peak, such that we get a higher binding energy per nucleon for middle-sized ones. We can achieve middle-sized ones by sticking two little ones together or breaking one big one up broadly, and that's the process that we go through to extract that energy. B does say from first principles, just like we said earlier, start with a conservation statement for neutrons, turn that into a differential equation by including a constitutive law. So what would be our constitutive law in this case that or law is the wrong term, but whatever constitutive relation we would introduce?
Fick.
Pardon?
Fick's law.
Yes. Yeah.
Sorry.
Yes, go ahead.
Okay, the neutrons are produced at the volume of the surface.
No, that's the conservation statement. Sort of what goes in must come out, or whatever that, the equivalent to that, and that would be div of j, the rate of flow away of neutrons is just equal to the local production rate, give or take any rate of accumulation or loss, the d by dt term. That's the conservation statement. The constitutive law that we introduce then will be to relate together the neutron number density, which is the thing that was changing or not changing if it was steady, and the flow of neutrons, and the relationship that gives us something, or the way we can connect our number density of neutrons and the flow of neutrons is Fick's law, which our gentleman here offered, which is our diffusion approximation in a nuclear context. J is minus d grad phi. So it says explain new concepts, e.g. cross-sections, neutron current as you introduce them, and identify the boundary conditions and explain their physical meaning. So again, I think if you've been in the same room as me much in the last 10 weeks, that ought, I hope, to be fairly straightforward. Okay. And note the limitations on any constitutive law. Well, diffusion approximation is a bit dodgy. It relies on sort of multiple collisions and so on, which for everything to have settled down and to become statistically okay. So we don't expect it to give a good answer within a mean free path or two of a point source or a strong sink, because there haven't been enough collisions going on to build up this kind of quasi-equilibrium statistically representative behaviour. If we're closer than a mean free path to the edge, it isn't going to be a good model. That's all it is. It's a model, an approximate model of the real world, and it's not a good one under those circumstances. So too close to a boundary, too close to a strong absorber, too close to a strong source, they're the places where the constitutive law has limitations. And then the final one was an absolute, from the notes, bog standard, solve the equation you've just described, derived for a point source in a weakly absorbing infinite medium. And we've done that. And what were the various approaches we identified to finding the arbitrary constants for that? What physical principles were those approaches based on? We've got our differential equation, del squared phi and minus phi sigma a and so on. There's no source, no fission source, and there's no source in the sense that we're excluding that point source and we're solving in the region around it. So that's a nice simple equation. So it's del squared minus 1 upon L squared phi equals 0 was the equation we solved. We generate a couple of arbitrary constants when we do that, when we integrate up, and we had to apply some physical common sense to identify physical principles that we could use to get our arbitrary constants. So what were those? What was the approach that we took? Or we used two alternative approaches.
No spatial
No. We're solving outside the point source. We're solving our differential equation, which is del squared minus 1 upon L squared phi equals naught. That's obviously, it's like the equation for the reflector outside a spherical thing. So we solve that and we end up with, I'm going to sound sad, I think it's a e to the minus r upon L upon r and b e to the plus r upon L upon r, isn't it, from memory? We get an a and a b constants of that kind. And we then have to say, what physical observations can we make about our system to get actual values for the a and the b? Not infinite, yep, that's a good one to go for. Grab the easy one first, that's a wise move. Yeah, so we got rid of the one that had e to the plus r because that can't stay. And we were then left with the e to the minus r upon L times 1 upon r from some, I think that is it, from memory. So what physical observations did we make to try and get that? What do we know about our system? I've got a point source of a certain strength in the middle. Because if I don't know the strength plane, I can't get an answer, so we must do whatever strength it might be, S naught, let us say. What do we know about our system? I've got a point source of strength S naught sitting in the middle of an infinite block.
You get the current by taking that source and spreading it over the area.
Yes, I can get the current at any radius shell that I choose. That certainly is true. Yeah, you're on the right lines. And so how are we going to make use of that observation to...
And then you take R to 0.
Yeah. So we can get the current as we consider a smaller and smaller spherical shell. And how we're going... You're quite right, so but keep going. How are we going to use that to get a value for the constant? What must the current equal? Yeah, so that's how we'll get the current. We'll get it by differentiating our expression for the flux. We get phi equals a e to the minus r upon L upon r. That's what we had. So we can get the current, which is d by dr of that, essentially times the diffusion coefficient. So that tells us and if we integrate that over the whole circle, just multiply by 4 pi r squared, or whatever the area of a circle, of the sphere is, that current must equal the source strength of that little source in the middle as we consider the shell to be smaller and smaller and smaller. Okay, so that's one. The limiting value then of the total current flowing out over that surface must equal total current by the current times the area. The limiting value of that must equal the source rate. Every neutron that's produced from the source must pass out over that little sphere. That's all we're saying. So that's one approach, and it highlights the unsatisfactoriness of it, doesn't it? We are here merely saying, let's evaluate our expression which results from using the diffusion approximation, and let's evaluate it in exactly the circumstances where it isn't very good, namely close to a strong source. But, fine. The alternative approach would have been to say, well, as I go out towards infinity, the flux we know is going to drop to 0, they're all going to get absorbed. So the integral of the absorption rate from here out to infinity must equal the source strength. That's an alternative approach. And I know the local absorption rate because I know the local flux. It's e to the minus r upon L times 1 upon r times an arbitrary constant. So subject to the arbitrary constant, I know the local absorption rate. So if I just integrate that up from r equals 0 out to r equals infinity, that absorption rate must equal the source rate. So two alternative ways, just using physical common sense to get at that arbitrary constant. And I think that's... Yeah, okay, so you needed to use those there. Right, what is meant by a supercritical reactor? What is meant by a supercritical reactor?
One that is increasing in power.
Absolutely. Yeah. Shock horror. 2 reactors went supercritical yesterday in the UK. We should shut them all down.
All of them.
So as it says, should you discourage operators from operating their reactors when they're at risk of going supercritical?
Well, if you are not at risk of going supercritical, you don't have a reactor going.
Well, absolutely, yes. Yes, that was what... That is all we were asking to say, yes. If they can't do that, you may as well not be there and you're out of a job, Inspector. So, you know. As a regulator, would you be content as long as your operator kept his reactors a little subprompt critical? And why or why not? What about that one?
Usually not a little sub-prompt critical, probably about as much sub-prompt critical.
I think absolutely, yes. If you're just a little bit subprompt critical, I'd be running in the opposite direction as fast as I could. Yeah, absolutely. You want to stay a long way subprompt critical. Just like we often use sort of convenient characteristic lengths to measure things and so on, a very helpful, I think, unit of reactivity, which we called rho, you know, the amount by which K was above 1. The convenient sort of length scale for rho is actually the delayed neutron fraction, the 0.007. Because when your rho is equal to 0.007, i.e. beta, you know you've gone prompt critical. So to know what fraction of that you are is actually a really useful way to measure reactivity. And that's a common reactivity measure you'll come across. That is defined as $1 in just as the terminology, and hence to be 1% of the way to one critical, it's having 1 cent of reactivity. So then, because that's what matters to you really, it's how close to prompt critical you are determines the behaviour. The actual delayed neutron fraction might vary a little bit from reactor to reactor, but it's how close you are to that delayed neutron fraction that ultimately determines everything. It's a bit like having a characteristic time, like e to the t upon tau, where we've got some characteristic time for the response of the system. Here we've got beta is the characteristic reactivity when things really change, and fraction to beta then is what matters. So you'll talk about reactivity transients as being so many cents per second inadvertently added to your reactor, or so many dollars a second if it's a bad transient you're addressing. Right, so what's meant by that? Would you be content? Well, you wouldn't, fine. And then, okay, well, this is bog standard stuff from your notes. Develop the time-dependent behaviour of an infinite reactor. And it says start from that. Okay, well, infinite reactor, you throw big chunks of it away, and there's simple manipulations to turn those mu sigma f minus sigma a, k infinity, sigma a minus sigma a, so k infinity minus 1, and that gives us the rho. We've been through that, that's straightforward, line it to a booklet. And solve the equation above, which I didn't actually say explicitly, because there are 2 equations above, I appreciate. Solve that one, not that one. I guess if any brave person chose to solve that with extra credit, but I don't think that was no one quite. So solve that equation, so we just n equals n naught e to the t upon l, and so on. And comment on the desirability. Well, plain if it's got no delayed neutrons, we're in a mess, so it wouldn't be any good, so just discuss that. And it just asks you, oh, again, I think this is probably lifted direct from problem sheet. So it's, again, rewarding those, I guess, that have done the problem sheet. And it's saying, initially in steady, a sudden step of reactivity, how long until as much energy is generated as in some time t of normal operation. So that's, again, if you've done the problem sheet, plainly it's straightforward, but remember, it's energy generated, not power reached, that you're asked about there. So that would have been normal operation. Let's say it was doing that, and then suddenly at time naught actually did that instead. That's our power. So remember, energy generated is obviously that area. So what we're asking you to do is say, how long until that area equals that area, which only 1 second of normal operation, or whatever it was, t star or something, or t, that was big T. So what value t star of time are those 2 areas equal? That's all it was. So obviously the initial power just cancels out. You don't need to know what it was in watts or anything. So just integrating up that that exponential and solving to find how far out you have to integrate it to until those things are equal. So just, you need to know what you're doing physically, and then it's a fairly trivial bit of algebra to implement that. And yeah, that's page. I've got the work solutions here to show, but I don't think we gained a great deal more than from having talked. I mean, do tell me if otherwise.
The one, the point source one,
Yeah.
or even just where it in the notes is.
Oh, yeah, in the notes, it's this is the physics notes.
Is- Nothing there.
So I help identify. Here we go.
Yes, but
Okay, sorry, yeah, the point source, there are two of those. Having derived the equation, we solved it collectively in your notes for the planar source. And the point source was one that I asked you to work through in the class on your own, and I then put up the printed solution on the board to confirm yours. So I hope you got a handwritten version when you did that, yeah. So yeah, but I know we've gone through it a couple of times with it up on the board. So, yeah.
With the point source one again, you said there was two different ways that you could either go. You could like integrate from zero to infinity with the absorption, or you could do
The limiting current.
the limiting current. Do you have to show both of those?
Well, no. I mean, if I ask you to find the answer, I mean, you find the answer. It's up to you to do, unless we said, do it by both ways and show they're the same, I guess. But if you can say that, no. Yeah. Speak up so we can all. Yeah.
For the very final question about time taken to the very last question.
Okay. Yeah. That one.
We see the steps in the solution. How many steps would you expect to see? Would you expect to see that graph that you drew on the board?
Well, all that we need, simply put down enough to help the marker, who I can assure you is normally looking to find opportunities to give people marks. Just make it clear to him that you know what you're doing. I mean, for heaven's sake, I'm not suggesting you would or anyone would, but it does happen. A question like that says show this result. It's amazing how many unbelievably tortured derivations going absolutely nowhere suddenly recover towards the end and actually please. It does happen. Well, I mean, it does happen, obviously, yes. I mean, so yeah,
my friend once put that, he got stuck, and he just put magic, and then the answer, and he got full marks. What? Yeah.
So we've seen the steps in
So nearly exactly got one thing wrong.
I don't know. Oh, well, we'll have that.
Would anybody else like to do that question E there, that one?
Derivation.
Yeah.
I'll put that. If someone just asked at the front, so I'll stick that up on the board. But you've had that as a problem sheet, haven't you, as well?
I can't recognise that.
No, I don't recognise gamma. I don't know what we're talking about here.
I don't recognise question B.
Yeah, I don't think we do.
What's gamma? It's a new baby on the block.
We can argue about it. Anyway, I wait to be proven wrong, I'm sure,
But even if it is, we don't have the solutions to the problem.
Yeah.
So we can't tell if it's right.
yes, you're quite right. Like you're now got to be.
That's the same question as 2013.
It makes me want to die. You forget to issue the problem sheets. Isn't it? Yes.
That's what happened last year.
No, you're right. I must have. I've taken it out from the problem sheet, so I withdraw that. Let's find the solutions then. Okay, so this is the solutions to the whole paper there. first part was just the, yeah. Okay, so that's all it was. So that's that there. So the power was given by. You were asked earlier to derive the solution to that differential equation, but that's just write it down. There's not any derivation. So P equals P naught e to the gamma over L times T was the solution to that time dependence. So the energy by some time T star, just E brackets T star, was naught up to T star, just integral of the power. That's just integral under there. So we just put in do the integral. It's the integral of that. Is that there? And what we want is that E at some T star equals the P naught times this T. So just setting those two together, it's a straightforward algebraic thing there, and it just drops out then. The only difficulty, I'm not being rude to anyone, you've got to integrate an exponential, but I'm sure that's we've already established that most of us integrate a cosine this morning, so we're on to a winner. The intent really is, if you've done what's in the course, and do sometimes do, not with this class, I confess. I don't mean this year's class, but not with direct physics. But you do sometimes think when you mark it, has that little sod ever been in the same room as me at any time in the past 20 weeks? You know, I mean, I'm sure it won't be like that for this class here. And I wouldn't say little sod about him even in his absence. I apologise.
Well, if he's not here, then he won't know.
Politically incorrect, absolutely, yes. Yeah. But you think, how could you say that? Right. Okay, did that meet that need to see the algebra there? But all we are doing, we worked out the power versus time, integrated up to some T star, and equated to that other and solved for the T star. Okay, so if that's useful, I could do the same thing for another year. Would that be a useful way to spend a few minutes? Mark, I'm in your hands, so please make sure that you do what's best for you folks. What are delayed neutrons? Well, we've gone through that at length. I'm sure everyone can tell us at great length. Discuss the safety issues associated with them. What's meant by the infinite multiplication factor? Mu sigma f over sigma a, and similar question but in different words, I guess, from the one we had before. Just discuss K infinity and how we improve it a little bit. Yeah, well we had the point source version and the previous one, this is the planar source, isn't it? That's derive the equation for the point source or the planar source and then solve it in the appropriate geometry. And that's what that one is, so rather than solve it for the point source, this is the one that's in the notes, and it's the plane source with the half space. So again, the absolutely straightforward bread and butter stuff there. Okay, I can go through that obviously in more detail, but I don't think that's going to be very efficient unless anyone tells me to.
For the first question, are you like expecting like as much as we're talking about in the passes and the notes and stuff, just so you have an idea?
Well, it gives a clue that says 200 words or fewer. I really don't want you to write pages and pages and pages. I won't read it. I mean, God, you don't need many words to give us enough. We're just looking to be confident you know what we're talking about. That's all. Well, this is rather more fun. Yes, this is lots of fun. I think it's fun. this is actually less bread and butter because this requires you to think, rather than just to be able to bring back up and bring back up. That was unfortunate. What would be teaching this question? I'll let you read that. Is that suitably legible? Do you need it bigger? Is that okay? Yeah, I'll shut up and let you read it for a moment. Obviously, the meat of the question is plainly in there in part B.
Just to clarify that.
Never stopped you yet.
On the side of the question is it absolutely necessary to derive the reactor equation when it doesn't say you do not have to derive it?
Is it necessary to derive it if I explicitly say you don't have to derive it?
Yes.
No, don't say.
Oh, I see.
Because it often says derive from first principles,
Yeah.
which could be easily mean derive the reactor equation first and then.
Yes. I think you just have to see what the individual question says. But again, we don't. It's not setting up artificial hoops to jump through. I'd have done that trying to discourage you in this case, just because there's plenty to be done going forward from there. That's all. I wouldn't have minded if you'd remembered it, or if it isn't given, and we don't say from first principles. It's generally fine to quote it if you can remember it, but it's not a memory test. I would have set the question within mind that the 2 or 3 lines to derive it is fine as well. So, yeah. But here again, just to make absolutely clear, I didn't want people distracting themselves too long there. I just thought I'll give you that and tell you can use it, but give it to you as well as say, and you can start from there. You can. So del squared plus b squared is naught. So this was the interesting part, wasn't it? That's straightforward. Criticality condition for a bare infinite slab. That's one we did first of all, the cosine. But the next is to do the criticality for a reflected slab, essentially. So that's relatively unusual that we can even find a topic that's not too unreasonable to ask in an exam, but which goes beyond the algebra we've forced down your throats during the course. I was quite delighted to come up with that. So it's, yeah, it's not difficult. It's very like the sphere. It's probably easier. You ever so sort of screwing your face up thinking that's not fair, yeah. Have a go at it, it really isn't. Have a go at it.
It's only an hour and a half to do this section.
4.5 hours.
Just because.
You've had a go at this question,
Yeah,
have
I've
you?
done it, yeah.
Okay, well, the thing to have done would be to get out your reflected sphere and say, could I do it for a reflected sphere if the question had been that? As pragmatically, that's the thing to do, because it must be pretty simple, hasn't it? It's 1D attached. The sphere is slightly more complicated because it's got an extra 1 upon r type term, otherwise it's the same. So, if I was struggling with that, think, right, how would I do it for the sphere? Must be pretty damn near the same. And if you do it for the sphere, I think you'll find it's easy. But I've got a solution here, so if it would be helpful for me to stick up that solution.
Have you done it? Yeah,
Taking all of this stuff and make it into that.
Okay, so we went through it for the bare part. I assume we don't want me to go through that together now. That comes up with the b squared is pi upon a squared. That's our simple slab reactor. The reflected, well, the solution in the core is the same as before, of course. So a cos bx the reflector equation just like the sphere. So if you've gone back to the sphere, it would have been exactly the same. Del squared minus 1 upon L squared. So we've got the, much like we had the point source a moment ago, we had e to the minus r times 1 upon r. It just is missing the 1 upon r bit. So e to the minus x upon L and e to the plus x upon L. As ever, C goes because we can't have the positive exponential. So we're left with that for the flux in the reflector. We've got there for the flux in the core, and we're just going to have to match at the boundary. We're going to match the flux and match the current. Again, no different from what we did for the so find the core, find the reflector, so that equals that, just putting in A over 2, which was the where the interface was, slab of thickness A, so A over 2 there. Matching the currents, i.e. matching the D times the derivatives, gives us that there, but again it absolutely follows step by step with the sphere.
Then it gets fun. Just making sure everything is perfect. I don't think it's like something.
You did get to there and then spend 4 hours.
No. It still took me a good 10 minutes to tidy it up properly.
Well, we had 2 equations. I mean, I haven't seen this for years, but we had 2 equations there, 1 and 2. And we took A from 1 and put it into 2, whatever, and just tied it up. We got an A. So either A is 0 as ever. So again, so those, we had our non-trivial solutions requiring that, and again, we plotted it using a graph. Okay, say relatively rare that, well, I at least find I can actually think up something that involves an interesting bit of new algebra that isn't also a part of the course. But I think that's an interesting, your friend's comment there. Step back and think about it. It's got to be, it can't be that different from everything you've done. You know, we wouldn't be doing that. And we had just talked 2 minutes earlier, as it happens, about the, in 2 successive years there'd been the point source in the weakly absorbing scattering medium, and then the next year there was the planar source, i.e. the same algebra, slightly different form of the, well, I guess of the Laplacian, resulting in a slightly different form of the solution, namely there's an extra 1 upon r, or there is a 1 upon r when there isn't one otherwise. But other than that, exactly the same, and the same physical observations that we'd use to get the arbitrary constants. Because for the planar semi-infinite case, we can have the limiting current and the total absorption, of course, in just the same way. It's obviously exactly the same physical statements that we can make. That's right, we went in to look at the solutions for just the one, didn't we? Obviously, Pond criticality, so that's one of the, it must have been a numerical question. I'll find that again. 2010.
So I was going to find the maximum width of the rectangular array.
That one there. So if I just find that question.
You've got you've got a rectangular reactor, and we
Yeah.
did one last night.
Oh, we did that.
Yeah, because you've got a block, you haven't got one of the dimensions, and you've got to calculate it
Yeah,
from.
okay, that's right. So it's a bog standard, put the numbers in kind of thing. We've got criticality condition on the cuboid, I think it is. If you get, I would strongly urge, I know I keep saying this, if you've got numerical things, I don't put many species in because, I mean, we're not interested in how good you are at arithmetic. I would urge you to do it in a columnar form because you're just much less likely. I mean, it drives me mad. You see something like k infinity equal this great long fraction. This times this plus this times this plus this times this all over the top and this time all over the bottom. And the chance of the right numbers coming out at the end is generally quite low. Because at least if someone does it, you can see they're trying to do the right thing and you've got more of a chance of getting it right. So I would encourage you to do that. And okay, this asks you to put in the numbers, work out that. What boundary conditions are implicit in that analysis? Well, using the bare, simple-minded criticality, your fuel was sitting in an infinite vacuum universe, but actually it's surrounded by water. So, as it says, the critical size would be reduced by reflection. Estimate how much that would reduce the critical size and therefore the new array, the new tolerable size of the array. Well, we've done that for a sphere. We said for a big sphere, when the reduction in size is not too big a fraction of the sphere, about 1 diffusion length, and it's going to be not very different from that regardless of geometry then. You know, if you took a centimetre off a 5 metre sphere, it's not going to be very different from a centimetre off a 5 metre cube. It's got to be from physical arguments. So sticking with that as an approximate measure then, it says you can do that. And suggest a modification. This is remarkably prescient, wasn't it? I think it was slightly pre-Fukushima. A modification that will allow an array with larger dimensions to be used. If you're a safety inspector, how would you view your suggestion? So what suggestion might you have that would allow a bigger array to be used safely in that fuel storage pond?
Surely it's more subcritical if it's larger. So we thought, well,
It's more subcritical if it's larger.
yeah, that's what we found yesterday, wasn't it?
Yeah, if you've got a lump of critical material and you expand the volume that's taken up.
Oh, see. Ooh.
Is that
Okay.
incorrect?
Yeah,
No,
so
no.
you change the
No.
composition.
What we're here, you're storing fuel rods, you're racking them in a pond, which is what you actually do. That's what the question's about. And what we're saying is, and this is a real problem for real reactors all around the world because no one sorted out reprocessing. They have to store more used fuel elements in their ponds. So what we're saying here, what modification can you suggest that would allow you to store more used fuel elements in that pond? That's what it's asking, isn't it?
The same size, but
Oh.
you stick more stuff in it.
Is that what it is?
Yes, an array with larger dimensions, yes.
That's a pond spec.
Yeah.
More stuff in.
Well, the pond's certainly bigger than the array, which it would have to be.
Boron?
Sorry?
Use a cadmium made
Yeah.
rack.
Yes. Well, both of those. Yeah. One chap here suggested add some boron to the water, I'm assuming, yeah? And someone else said make the racks that you store them with include some cadmium. And both of those approaches can be used, would be used. And then you've got to think, well, okay, well, is that safe? And this is where you have to sort of think, you know, what could go wrong if everyone was really stupid or very unlucky. Let's say your pond leaks, like at Fukushima, so someone gets his fire hose out and tops it up again, because it's going to overheat. Well, you might prefer to have a slightly overheating set of used fuel rods than an inadvertent criticality, because you've suddenly got unborated water. So these are the sort of issues. Yep.
So we did this question yesterday, and a couple of things came up. For first part C, we had a friend who did reactors last year, and we realised that actually, if someone's doing this question, it's important to note that when you expand the size, it has to go in all directions, not just one direction. Because a lot of people, we were thinking very physically last night, as a physics buddy, rather than from an engineering
Firstly, part C is
The
about
holes,
is reducing it. Isn't
Sorry,
it?
reduce.
Yeah.
And secondly...
Yes. So yeah, the sphere, it was the radius, which
Yeah.
is equivalent to.
Yeah, see, we didn't do that initially.
Yeah, okay.
Why are we getting those? And secondly, Will and I both did it in tandem,
Yeah.
and I was using a calculator, and I like to use all decimal places, and he was using like 2. The answers came out like radically different, which is because of the fact you're doing squares of pi over and stuff.
Yes, and you're looking things like k infinities.
Yeah.
And it's the surplus above 1 and so on. So yeah, it is unfortunate because inevitably there's a big uncertainty in the numbers and you end up needing to do something quite precise with them.
Yeah.
And I'm conscious never necessarily in sort of questions in a teaching context, it's sort of a bit contradictory because we give you models and so on which aren't all that accurate, and then but to evaluate them and get sensible answers you still have to do the sums carefully, and there's a sort of there's a built-in conflict which you can't do anything about. We're stuck with that. So yes, you do need, because you're going to, it's quite an ill-conditioned calculation, isn't it? K infinity minus 1. You've got to get the K infinity quite close for the surplus above 1, because it's close to 1. So you've got to get it pretty accurate in its own right for the reactivity bit to be at all accurate.
So keep as many decimal points as possible.
Yeah, I mean within reason. Yes, yes, yeah. I mean,
So, surely if you go step by step, say he does 5 decimal places,
yeah.
and I'm saying, well, the more decimal places I'm doing, the more I'm likely to press the ball back, and I just do 1 or 2.
Yeah.
The steps are exactly the same.
Yeah.
I'm consistent all the way through. Surely, and he gets an answer of K infinity of 1.3, and I'll get it 1.2. Does it really matter if you've got it correct in principle?
Yes, you're right. It's just that you don't have to go far, and you could be correct in principle, but have literally the wrong answer, like saying it's subcritical when it's supercritical. So I take your point, but in one level you could say about any numerical question, well, I've done the algebra, so I've shown I know what needs to be done, so why do we have numerical questions at all? It's not far off saying that, and which is a perfectly valid question. Why is that?
It's just unfortunate. Effectively, isn't it? Gravity's 10.
Well, that explains a lot, doesn't it? Yeah.
It's just unfortunate that the equations that you have to plug the numbers into are just so...
A bit sensitive.
Yeah, it's very...
But I mean, that of itself is an important thing to know, that these things matter, and it tells us how demanding, say, we are of the quality of our data. Okay, it's 10 past 10. I'm happy to carry on or pause for a gap. So collectively, you choose. Pick another year and go through the paper. Again, whatever you find helpful. So please, I'm totally dependent.
Pick another year.
Someone say something. I'll go to the next year if that's of interest.
Can I just so for sealing access to is that using material from the previous question when we did the reflector?
I think you've worked out enough for this composition by then to know what the diffusion length would be for that material. Well, you must have done. You've done K infinities and everything. So no is the short answer.
Yeah, okay, no, I haven't read the main thing. I was reading.
So, Simon, so this is also like thinking the work that we did for a sphere and just applying it to a...
It requires you to know that, as a general approximate observation, a reflector will reduce the critical dimension by about a diffusion length. Yeah, absolutely so. Yeah. So it's not fair to be expected to remember that when you could have gone away and derived it for the sphere if you really needed it.
So the diffusion like L, right?
Yeah. But that was the conclusion we came to when we looked at it. Right, I've got another one. 2000. So again, you'll see that sadly there's only relatively limited number of permutations we can make on the various things in the course, but that's fair enough. Is that the logic? That's the logic. Okay, well that's first that derivation showing about the relationship between criticality and non-leakage probability and so on. That's fair enough. That's in your notes, and we derived that together in the notes. Yeah, and we come up with the observation that the K infinity times the non-leakage probability equals 1 is an alternative way to think about, an alternative interpretation of the criticality condition, which physically it must, of course. I mean, the only difference between an infinite block of the material and a finite block is that from the finite block you'll get some leakage. So it must be the case that for the finite block to be critical, what would have been the multiplication factor were it infinite times the fraction that actually stay in it must be 1. That's all we mean. So it follows almost from the definitions. And then it says just compute the numerical values. So we have to compute basically the L squared and the BG squared, the K infinity minus 1 over L squared. So D upon sigma, you need to compute sigma A and K infinity and so on. Basically that same old table with sigma A and mu times sigma F. And once you've got those numbers, the rest follows. And again, only 4 components. I mean, plainly it's a ludicrously overly simplified example, but there's no point in putting in more components just for the sake of it. No, that was just a slight inversion of the normal way round. But yeah. So therefore, for that reactor, just inverting it a little bit. So was that subcritical or supercritical? We normally say what dimension would it need to be critical. It just is a slight flipping of that normal exercise. Okay, 100 each maximum words. So explain what we mean by prompt as opposed to delayed neutrons. So what are they? How are they significant? And talk about reactivity feedback, prompt and delayed feedback. Slightly mischievous there because plainly we're using the prompt and delayed in the third part in the context of feedback, which is different from the prompt and delayed in the context of neutrons. But again, we've talked about that. It's a clear physical distinction. It's not just playing with words. We're talking about different things. So I don't think that's unreasonable. So I hope you'd all think, well, that's okay, fairly straightforward. If we've been in the same room very often in the last few months, we're okay on that one. Discuss the main features. So what would we say? Well, the graph is telling us quantitatively the probability of fission by neutrons of different energies. We see the probability for fast neutrons is orders of magnitude smaller than as it gets slower, and so on and so on. Discuss that. Then you just talk a little bit about the messy bit in the middle. And then B, ask you to discuss which are the main cross sections and talk about microscopic and macroscopic. Just plainly they both feature, they're connected but different, obviously. So, the meaning and the dimensions of the two forms. So you can point out the oddity. We're talking about cross sections with dimensions of length -1 there. Square meters per cubic meter. Sort of similar in a way. C. Distinguish between neutron flux and neutron current, and again we've gone through that extensively. So I'd hope this. I think that was fairly straightforward. And yeah, so D basically says write down a conservation statement and introduce a constitutive law. And then the final bit says, and tell us what's dodgy about the constitutive law that you've introduced. Again, we've talked about that already, I think, this morning. I'm seeing all these as they come past thinking, oh, this is too easy, we're going to have to do something to stiffen up the course a little bit. Too late for you, those. Absolutely put the numbers in. You've got the criticality condition in your notes, so if you remembered enough to be able to work out sigma A and mu times sigma Fs and K infinities, you just put the numbers in and go through. And if we tell you diameter equals height, fine. And again, it asks you to use that approximate knowledge of the significance of a reflector to give an order of magnitude indication of how the dimensions would be changed by having a reflector.
Lots of diffusion length of each face.
Yes. Yeah. So once off the radius, then effectively, twice off the diameter.
What's the logic behind that?
Of saying that our result for the sphere will be reasonably okay for the cylinder. Was that the question?
No, why is it one diffusion length?
Oh, well, it dropped out of the algebra we did for the spherical reflector. Do you remember we looked for the critical condition for the reflected one, which was the intersection of the y equals the tangent and y equals a constant, and we looked where that intersection was, and we saw that we could demonstrate that that intersection was always at a slightly smaller radius than the critical radius for the bare sphere. And then by looking at the little bit of sort of trigonometrical approximations, broadly that sine x equals x for small x, by using that observation, we could make a reasonable estimate of by how much the radius had been reduced. So that's the final third of the notes on the reflected spherical reactor part. Yeah. Okay, that was like the last bit of criticality type stuff we did. And that gave us an indication that the reduction in radius was about one diffusion length for the sphere, and as long as that one diffusion length was small compared to the overall dimensions, it wouldn't be desperately different for other geometries, because it's a more local effect than that, as long as the thing overall is quite big.
Yeah, is it just the algebra proves that, or is there a logic?
Well, no, there's two parts. There's that it is a diffusion length for the sphere comes out of the algebra. And the algebra has all the caveats about actually it's a bit approximate, but fine. The saying, well, it's a reasonable approximation for other geometries, comes out of hand-waving physical common sense, no more, no less than that. If you think about if that reduction was small, so we've stripped off a centimetre off our 2 metre sphere, it's not going to be very different from saying I can take a centimetre off my 2 metre cube, because it'll be a local effect, it'll be leakage just nearby that's brought back in. The fact that there's a corner to the cube up here won't be felt by those neutrons. They won't be aware they're on a flat bit of the face of a cube rather than on part of a curved sphere. So that's the argument, and it's only a hand-waving argument, but it's a perfectly good one. You could demonstrate, if you could solve both properly, you'd be able to demonstrate numerically they were right, that it was a pretty good approximation. So as long as the reduction isn't big compared to the actual size, in which case then size does start, or shape starts to matter, you can make that approximation. So if you compute the diffusion length for that thing, we can say, well, and we've already said, I think, it's got the diameter is equal to the height, so it's sort of as near to being a sphere as a cylinder can be anyway. Like we've already said, it's a sort of squarish, square-sectioned cylinder. So it's a reasonable stab at it to make that same approximation. Okay, I have the solutions to those, so if there's any of those questions we're actually seeing the solution would be helpful, perhaps say now. I'll just scroll back up so you can remind yourselves. We had the numerical one talking about cross sections and so on, and then essentially develop a conservation equation and neutron distribution equation.
You have a question for? What's
Yeah.
the question for?
You'd like to
This question for?
You'd like to see question 4?
the access.
Sure.
Okay, the numerical bit's actually working out K infinity,
Yeah.
well done in a table, which I can put it up if anyone would like. So K infinity then obviously just that there. So the K infinity will actually be computed on my table. I'll have used a spreadsheet just as lazy or why not. So B squared was the K infinity we computed minus 1 over the L squared, which we also computed up there. And again, it's all obviously a table. Okay, and then just working out the criticality, well, we're told the height is equal to the diameter, so just putting in 2r instead of h, that just works through, so we get our b squared, very trivially, and that comes, from that comes our diameter and our radius. I think that's the end, or effectively the end. So we had L squared, table, we'd have computed in our table about 0.126, so the new D and H both reduced appropriately. That is the table. Okay, there's the table I was talking about, so there we go. It is, obviously mine would have been a spreadsheet, but if I was doing it by hand, honestly, I would still use a table. I think it's just a lot easier, less likely to go wrong. So there's the 0.126 for the L, for example, that featured down there. Okay, again, do we want to pause and resume? I'm seeing some nodding. So should we pause for 10 minutes, give people a chance to go and get a cup if they want a cup, and I'll carry on doing this or any other format